Welcome back. This is Module 10 of GIS Primer. Last time I talked about GPS infrastructure. Remember, there are three components to that. There's the space component, the satellites, the control component, which is the on-the-ground controlling the satellites component, and then there's the user component, which is the GPS receivers. This time I need to talk a little bit about GPS errors, because like everything else out there, there's errors associated with your data and you need to kind of understand what they are. You can get errors from the atmosphere. There's two main sources of error, the ionosphere and the troposphere. And so those pieces of the atmosphere are going to affect the signal from the satellite differently. And so when we use the basic equation that says take the difference in time and multiply it by the speed of light, turns out that those atmospheric effects can change the speed of the signal between the satellite and the receiver, and so it's not exactly the speed of light all the way through. Sunspots can mess things up. There's noise in the measurement. There's always random noise in your measures. Ephemeris errors, those are errors in exactly where that satellite or those satellites might be located. They might be really close. The control segment might know pretty close where they are, but not exactly. The satellites have clocks, atomic clocks. There's 4 of them on each satellite, but they tend to drift after a while, and since light travels very far in a very short amount of time, just a little bit of drift will cause an error. 1 nanosecond, the signal goes 1 foot. And a nanosecond is 1 times 10 to the minus 9th seconds. So you can imagine if there's just a little bit of drift in the clocks, that's going to cause error. And there are multipath effects. It turns out signals can kind of bounce off things, and when they bounce, they can hit the receiver having gone further than you would think if it was a straight line distance. Here's a chart that shows a comparison between the potential or standard error with a regular GPS, single frequency receiver, and differential GPS. And well, I'll talk about that in a minute. Clocks can be off by 1.5 meters with the standard GPS. Differential GPS is going to correct for that. Orbit errors could be 2.5 meters in standard. Differential going to be 0. Ionosphere 5 meters, 0.4, and you can see how things compare. Receiver noise and multipath effects are roughly the same in standard and differential GPS. Standard GPS is going to use 1 frequency for the receiver. Differential GPS is going to use 2 frequencies, and since different frequencies are affected by the atmosphere differently, then if you have 2 frequencies, you can kind of filter out the amount of error that the atmosphere might be causing. And so that's why differential is a lot better in that way. Clocks and orbits, that's going to come from kind of the basics of differential GPS. There's this concept called dilution of precision, and remember, everything is a triangulation of actually 4 satellites when you're figuring out your location. And so dilution of precision is related to where those satellites are that you're using to do the triangulation. Usually the rule is the wider angle, the more angle between the satellites, is going to give you a lower dilution and a higher precision. So you can imagine a satellite signal coming from the satellite, and it gives you a timestamp that lets you calculate that you think you're right about here, but there's enough error in that signal that you might actually be here and you might be here. So there's uncertainty in the range that you calculate based upon one satellite. If you have multiple satellites, each one will have their own uncertainty. So this satellite has this range of uncertainty, and that locates you somewhere in this band. This satellite has this range of uncertainty, and so you're somewhere in this band. And then the third satellite has this range, so you know you're somewhere in this band. And when you intersect all those bands of uncertainty, you're able to narrow down the fact that you're somewhere inside of this polygon, and that's your polygon of uncertainty, and that is your dilution of precision. So when you look at this, if you have satellites that are kind of close together and you intersect all of their bands of uncertainty, you see that you're going to kind of have a large polygon where you could be falling anywhere in that polygon and still fall within each individual satellite's band. If the satellites are widely spaced, you're going to have a smaller polygon, so smaller area of uncertainty. There are limitations to this because you can imagine satellites that are off in this direction are going to have to go through more atmosphere to get to the receiver, so they're going to have higher atmospheric errors. So it might be that wider apart is lower uncertainty in terms of precision, but it might be higher uncertainty in terms of other error sources. What's differential GPS? Well, here we have 5 satellites that the receiver is looking at, and we have another receiver over here that's looking at 4 satellites, I guess this is 1, 2, 3, 4. This one's looking at 5, this one's looking at 4. So two different receivers, 2 different points. This point, if we know where this is, because it's a surveyed point on the surface of the planet and we know the location of this point could be our unknown point. We want to know where this is. We don't know where this is yet. We can call the known point a base station, and then the unknown point we can call a roaming unit. So we're going to be able to get better accuracy by saying, well, we know where the base station is, and based upon the satellites, we can calculate what the receiver thinks the location of the base station is. There's going to be some error in that. And if we apply the same correction to our unknown point that we would apply to the known point, then we can get rid of some of the error between the two. So here we have a precisely measured position. Imagine just one satellite's being used, and the satellite tells you you're here, you know you're right here from survey, so there's this much error in what the satellite's telling you. Well, if you know that there's this much error in what the satellite's telling you, and you're fairly close, this point is fairly close to this point, you can assume that the satellite signal went through the same type of issues to get to the receiver, so you can say, I'm going to assume that the correction that I need to apply to my roving point is the same correction I need to apply to my known point, and that way you're able to get rid of a lot of that atmospheric error that you would have if you didn't have this known point to compare it to. Okay, so we have the known point and the unknown point. We can do this 2 different ways. We can do it in real time. If our base station has a transmitter, it can get the information, calculate the correction that it needs to apply, transmit that information over to your roving receiver, and you can apply that correction in real time to your roving receiver. So that's going to give you real-time differential correction. We can also do it in what's called post-processing. If the base station stores information about what signal it's receiving and what the correction should be based upon time, and you're storing your information, you can both upload your information to the internet, and based upon the comparison at exactly the same times between your receiver and what the base station would correct, you're able to post-process, do the corrections. There are these wide area augmentation system stations, and those are associated with airlines, and so these are locations that are close to airports, and what they're going to be able to do is do the equivalent of a differential correction. They're fairly widely spaced, but they actually send information out so that you can get corrections from the satellites based upon what the wide area reference station is using as its differential correction. The post-processing way you can do it is you can use what's called OPUS, Online Positioning User Service. That's where you store your GPS data. This has to be dual frequency data. There are these sites that have known locations that are collecting GPS information, CORS sites. Those get uploaded. You can take your data, upload it to the internet. It gets compared to the corrections that would be applied to the CORS base stations, and you get a highly accurate result that you can then get out of the internet and get post-processed corrections. CORS stations, there's a bunch of them. You can see in this map that there are a whole bunch of them. If I zoom in a little bit, I see in the northwest, there's even a whole bunch of them in the northwest. I'm going to zoom in a little bit further. Here we have Moscow. There's actually a CORS station up here to the north of Moscow off of Foothill Road. Zoom in even a little bit further, and there's the CORS station. So the location of this point is precisely known based upon a survey. It's getting satellite information and determining what type of error there is in that satellite signal based upon the difference between what the GPS would calculate and the known location. Stores that, uploads it, and you can use it to do corrections. You can do this online. It's free. You can upload your data file. You have to have dual frequency GPS, so a regular small handheld won't work. You have to have kind of a higher tech GPS receiver. You upload your data, and what ends up happening is you get corrected location data that is a lot higher accuracy than what you would have just from your standard GPS, because you're able to correct for a lot of the atmospheric effects. So here's an example of the solution, what you get back after you've uploaded your data and it's been compared to the core stations. You get X, Y, and Z locations, so we get heights, X's, and Y's, and you can see that we're getting different kinds of things. We're getting both ellipsoidal heights and orthometric heights. And remember from back in Module 3 when we talked about projections, the ellipsoid is that smooth surface. That's basically what the GPS is giving you. And based upon the geoid and where the geoid is at with respect to the ellipsoid, you're able to get an orthometric height. And remember, an orthometric height is one that measures according to mean sea level. So it gives you an energy height, which is what you want to do when you're measuring elevation. So as a review, remember that we have the smooth surface, which is the ellipsoid. The ellipsoidal height is what the GPS is giving you when it calculates the satellite distance. And then you have this thing called the geoid, which is the gravity height, the gravity model, right? And so the geoid height is based upon the geoid model that you use. This one is a vertical datum from 1988. Remember, there are different geoids. And so based upon the geoid height and the ellipsoid height, you're able to calculate the orthometric height, and that's basically the elevation that you want to use from mean sea level. Here's a map of the difference between the geoid and the ellipsoid across the contiguous United States. And you can see in our area it's yellow, which shows you that the geoid is actually somewhere between like 11 and 18 meters below the ellipsoid. So the ellipsoid's here, the geoid's here. GPS is going to calculate a location on the ellipsoid. You need to know what the geoid is to be able to get your elevation from mean sea level. Okay, that was a quick fly through of different sources of error in GPS. A good GPS will get you within maybe 3 meters. A really good GPS might get you within 3 centimeters, and a regular old GPS might get you within 10 to 30 meters. Next time I need to talk a little bit about land surveying, because GPS is used in land surveying, and so after next time you'll be able to see kind of how GPS might figure in collecting information of locations out in space. That'll be next time.